Hello everyone, today we are going to solve question number 19, remove nth node from the end of linked list. Given the head of the linked list, remove the nth node from the end of the linked list. Okay, so in this video I am going to discuss three approaches to solve this question. Okay, so let's see. First, majorly the goal of this question is that you'll be given a position and a linked list and you have to remove the node in this position. Okay, so basically you can see to remove this linked list node, what you have to do is you have to just adjust this pointer to the next node. Okay, so this is the final outcome where we are just adjusting the address of this pointer to this 5. Okay, this way we have successfully deleted this node and then we can just delete this node from the memory. Okay, so our secondary goal now becomes that we have to reach this node which is previous of the position that we are going to delete. Okay, so one thing I also want to discuss is that there could be a case where you have to delete head, and hence from our previous videos we have learned that we can use a dummy variable to solve all the head deletion cases. Okay, hence I'm going to use a dummy variable in this methods in almost all the methods. Okay, so let's see the first method. So the first method is going to be remove nth node from the linked list. This method is going to take a time complexity of O of n, space complexity of O of n, space complexity for the recursion stack, and as we are using recursive approach to solve this question, the core idea behind this method is going to be first thing that we have to reach the end. Then while backtracking, what we can do is we'll just decrease the value of position, and when the position reaches to the previous node in like this, when we reach this node while backtracking, we are going to just adjust the pointer for this node. Okay, so you can see of tasks here will be first reach the end of the linked list through recursion, and for that the base case is going to be node equals null. Then while backtracking will reduce the past positions. Okay, so we'll pass a variable named position and we'll reduce it until we'll reach point when we reach the position -1. -1 because we have to reach the previous of our position. Okay, so after this means we have reached the previous of the node that needs to be deleted. Okay, so this is going to handle case for us. And if you wonder what will happen if we intend to delete this first node, in that case we'll also have a dummy. Okay, so our previous our position -1 will reach at dummy and then we'll delete this head. Okay, so initially you can see some visualization here. Initially node or n position is equal to 2. Okay, after backtrack after all the recursions I have reached this position, and now from here while node equal null will return to this recursive call. Okay, where my position will be pointing to 5, and in this case after, for backtracking I'll do an n minus minus, so now n will become 1. Again for next call we'll have n minus minus, and n will now be 0. Now for this case we'll do another n minus minus, and now n is equal to -1. So in this case we have reached the previous, and now we'll update the pointer. Okay, so let's code this one. Basically first thing that we'll do is, you can see there's a case where we have to handle this one. Okay, where there's just a single element. So I'll just do this if not head, or you can write head equal null, then I'm going to directly return null. Okay, this is just fail case, although I don't think, yeah, I don't think we'll ever reach that. Okay, next thing we'll need a dummy. So list node dummy 0, and it will be connected to um, our head. Okay, so dummy dot next is equal to address of head. Okay, so now we have connected our dummy, Now what we have to do is we are going to pass it to a secondary function that is going to solve this for us. Okay, so it's going to solve, and I'm going to pass dummy. You can pass it like this also. You can directly pass head to it. Okay, address of dummy, and also pass n with it, and we received it from here. Okay, so now we'll write a void function solve, and let me complete this function. After this, we'll just return dummy dot next. So dummy has handled all of our head deletion cases, and okay, so this is for failsafe case. Next we'll have list node star head, or you can write node better, and we can write int and n. Why we need an and here? Okay, because we have to pass this by reference, not not pass by value. If we passed it by value, so if you pass it by value, then what will happen is we had n is equal to 2 for this one, it will become n is equal to 1, but for this again n will be 2, and then we'll again reduce it to 1, so it will never reach to n is equal to -1. Okay, so it's duplicated, the value has been duplicated. Okay, so we don't want that. So one thing, we'll have a base case here, we'll think about it later. So first thing that we'll need is we'll need a recursion. So solve nodes next comma n. Okay, and the base case will be if node equal null. Okay, so in that case we have reached the end of the linked list. Now it's time to backtrack, so we'll just return because we have a void function. Next we'll decrease n minus minus. Okay, so this is our backtracking part, because after all the recursions, backtracking. Okay, this is n minus minus. Now if n equal -1, in that case we can do list node star deletion, or you can write del is equal to nodes next. So I'm storing the next value that needs to be deleted. Now nodes next is equal to deletes next. So this is the reconnection part. You can see this, you can imagine del as this one and node as this one. So del's next, or nodes next is equal to del's next. Okay, this is del's next, and so I'm connecting this. Okay, so this, and in the end I'm going to delete del. Okay, so this should work, and this void function, so we don't have to return anything. Okay, let's run this. Okay, so I should have pointed to it like this. Okay, let's submit this. So you can see we have solved this question using recursive approach. This method takes a time complexity of O of n and space complexity of O of n. Now we'll see the second method, the length based method, to solve this question. So now we are going to see length based approach to solve this question. Okay, so in this approach, the time complexity is going to be of n and space complexity is going to be of 1. Okay, the core idea behind this method is, rather than reaching the end of the linked list, what we can do is, first we can create a variable that's going to store the length of the linked list. Then we are going to traverse till the n minus 1th part. Okay, so basically from the end I'll reach this, from the starting I'm going to reach this part. Okay, so to calculate what position it is, we'll need a length, that is the length of the linked list. Okay, so after reaching this point, I'm going to reconnect it according to the demands of the question. Okay, so the task in this method is going to be calculate the length of the linked list, traverse for length minus n times. Okay, so once I reach here, I can just remove this pointer or this node. Okay, then I'm going to reconnect according to my deletion requirements. Okay, so you can see the same case. Initially n is equal to 2. I'll calculate using a for loop or a function which is going to calculate length for me. So for this linked list, the length is going to be 5. So you can see n is 2, k is 5, 5 minus 2 is equal to 3. So you can see position 1, position 2, and this is position 3. Okay, so I've reached position 3 using this formula. Next, after reaching this position, I'm going to reconnect nodes according to this. Okay, so let's code this one. This is a very intuitive approach because you obviously know that you cannot traverse backwards in the linked list. So what you can do is you can calculate the forward position of node deletion. Okay, so rather than the question demands us that remove nth node from the end of the linked list, I can calculate that same position from the front of the linked list and then delete this node. Okay, so let's code this one, and this method is obviously possible because we have these constraints that help us to like uh, we cannot go out of bound with this method. Okay, so let's see. First, let's handle the length part. So int k is equal to, I'm going to write a function get len head. Okay, so this function is going to calculate us the head of the length of the linked list. So this is very standard function get len list node star head. Now I'll use a count variable is equal to 0. I'll also need a temp, so list node star temp. I can use same head, but okay. So while temp is not equal to null, I'm going to increment count. So count plus plus, and temp is going to move to the next node. So temp is equal to temps next. Okay. After this, we can just return count. Okay. So this is going to give me the length of the linked list. So I have length of the linked list with me, and I can also calculate times. So how many times do I have to move forward? Okay. So to calculate that, I can just simply use n minus or k minus n. You can see here k minus n, which is going to give me a position 3. Okay. Next, to handle the head deletion case, we'll need list node star or list node dummy, which is going to be 0 list node star previous is equal to dummy, and dummy, and let's connect this dummy to dummy dot next is equal to head. So now dummy is connected to our list. Previous is pointing to dummy, and list node star current is equal to head. So current is pointing to the head of the linked list. Now while times minus minus. So what this is doing is I have pre-calculated the number of times that I have to traverse from the starting of the linked list. Okay, rather than from end of the linked list, I have pre-computed it. Now what I'm going to do, I'm going to move previous and current for these many number of times. Okay, so previous is equal to previous next, and current is equal to currents next. After these, what I'm going to do is I'm going to move the pointers for previous. So previous is going to reach this position, okay, and current is going to reach this position, okay, the fourth position, and previous is at the third position. Now I'm going to reconnect. So previous next is equal to currents next. So this is going to reconnect. So previous next is going to connect to currents next. Okay, current is this one. So currents next. Now I'll delete currents. This is going to free up the memory, so we don't have memory leak. Now we'll return dummy dot next. So we have also handled head deletion case. Okay, let's run this. Okay, one thing that I should mention is, although we have passed this test case, I'll explicitly write two things that if, okay, I have to write it after k. If k equals 0, return return null. If k equal 1, although this should not be the case because we have constraints, but simply if we had some other constraints, we can just use return null. Okay, so let's run this one too. Okay, let's submit this. So we have solved this question using a length-based approach also. Now we're going to see the third method, which is almost the same as this one, but the question demands us that could you do this in one pass? So yeah, fast and slow method can do this method, do this question using one pass. Okay, let's see that. So now we are going to see fast and slow pointer, which is the best method to solve this question. Okay, so let's see how it works. This method is going to take a time complexity of O of n and space complexity of O of 1. The core idea behind this slow and fast pointer approach is, initially, after initializing both of these pointers, I'm going to move one of these pointers fast, most probably, to n nodes ahead of the second one. Okay, the slow one, I'll move fast one n times ahead of it. Then I'll move both of these pointers together till fast reaches the end of this linked list. And once uh, fast has reached the end of the linked list, I have correct position of slow. So by moving both of them together, now I'll reach this position. Okay, you can see this position we had in our last case for length based. In the length based approach, we had this case where we have to reach this position. Same way, slow is going to reach to the correct position. Okay, so task to solve using this method is initialize fast and slow pointers, move fast pointer n times ahead of slow. Then now we're going to move both of these fast and slow pointers till fast reaches the end of this linked list. Okay, once fast has reached the end of the linked list, slow will be at the correct position to delete the next node. Okay, so you can see the visualization. Initially n is equal to 2. I initialize them at dummy, not at head. I'll initialize them at dummy because there can be a case where I have to delete head. Okay, now I'll move it by n times. So I have moved it to this position. N is equal to 2. So 1 and 2. I've moved it to this point. And now I'm going to move both of these, slow and fast, together. Okay. So fast reaches 3, slow reaches 1. Slow reaches 2, fast reaches 4. And you can see slow reaches 3, fast reaches 5. Now we can stop here. The stopping condition will be fast next is equal null. So this is our end of the linked list. We have reached the end of the linked list. Now we can just repoint this slow to this next one. Okay, this is just a coincidence that fast also points to this node, but this won't be always the case. So you just have to use slow to reference to this node. Okay, so let's code this one. So first we'll need a dummy. So let's node dummy 0. Then I'll connect it. So dummy dot next is equal to head. Next, we'll define two pointers, slow and fast. So list node star slow is equal to address of dummy, and list node star fast is equal to and dummy. Okay. Now, what I will do is I'll move fast by n times. Okay. So for int I equals 0, I less than n, I plus plus, fast is equal to fast's next. Okay, so I've moved fast. Now what I want to do is I'll do yeah, now I have to move both of them. So while fast next is not equal to null, so this is a stopping condition. Slow is equal to slows next, fast is equal to fast next. Okay, so this is it. Now the final part is it's optional to delete this 4. Okay, this 4 is not required to be deleted specifically, but we can do some good practices. So list node star del is equal to slows next. Okay, so since slow is at 3, slows next will be at 4. Okay, what I'm going to do is I am going to update slows next is equal to fast, oh sorry, slows next is equal to del's next, and then I'm going to delete del. Okay, and in the end I'm going to return dummy dot next, so that if we are deleting it, we can return. Okay, and maybe I should consider for these two cases that uh, if head equal null, return null. Yeah, let's run this. So this is just to delete that 4 node. It's not mandatory. You can directly write, in this case you can directly write slows next is equal to slows next. Okay, you can also directly write this, but I also like to delete that node so that we don't have a memory leak. Okay, so that's it for today's video. We have solved this using all 3 methods. Thank you.